Okay, now the reason for showing this is we've got a grant application that's about to go in with the EPSRC and the Norwegian Re Research Council. So I thought I could fill half an hour with this. And if anyone sees any howlers or mistakes in logic and things, then now's the time to scream before the referees ravage us, which they try to do, don't they? We all know that. Right, so this is basically a talk behind the application, developing and assessing bio-based consolidants for archaeological wood, with prime focus on maritime archaeology, such as the Viking ships in Oslo and the Mary Rose in Southampton. Not just the ships themselves, but the artifacts that are often found with them, and using some amazing, I say, bio-based crabs. I've got sand here. That's not really bio-based. It's natural. And from that, actually, was the okay. Sand. There's lots of sand, so we can get silica and these molecules called siloxanes, which have been considered as consolidants for archaeological wood. And Michelle, you might remember Michelle, she did a nice paper on this a few years ago. But the focus now is on these molecules, terpenes, with Rob Stockman in the chemistry department, because of great tunability and the fact they can be attached to a polyacrylate or polyacrylamide backbone, which is far more stable than the glycosidic based beta-1,4 glucans, which natural wood is based on. And this is the basis of the UK-Norway grant about to go off. It's a joint scheme between the EPSRC and the NFR. In fact, it's the same scheme that Gordon was PI, and we were on this along with groups at Liverpool and Oslo. This joint scheme between the EPSRC and the NFR, which in a way compensates for Brexit and things. I know we're allowed to take part in Horizon and things again, but you can't help feeling that our European colleagues, when it comes to refereeing applications with a UK team on, you can understand if they're slightly biased against us, but that doesn't apply to the UK Norwegian scheme. So it's almost ready to go. I'm not going to explain all this, but it builds on earlier work and contributions of 4 PhD students. Sorry, Jennifer, I'm embarrassing you here. But Emily, some of you might remember Emily, actually. She was here before COVID, Emily McHale. She was based in Oslo, where she did her PhD, but she spent lots of time with us working on lignin-like isogenol polymers. Then there was Yudong, who was working on lignins, and Jennifer, focusing, when she did a PhD anyway, she was focusing mainly on chitosan's aminocellulose and derivatives thereof, which made them soluble in non-aqueous solvents. And then Michelle, who focused on terpenes, but also looked at other polymers as well, such as the siloxanes. So it's thanks to these PhD students and the great work that they did that we can now form the basis of this application. Of course, Jennifer went on to other things as well. She spent a year at Celtech and then took this TexRec postdoc between Norway and ourselves. That was focusing more on textiles rather than archaeological wood, and she talked about that a few weeks ago. And then these 3 PhD theses online. We're still waiting for Yudong to write hers up, so hopefully that won't be too long. And these are just some of the examples of archaeological wood which does need consolidating. Because Jennifer explained when she last gave her talk, they look great outside, but that's only because of the outside lacquer and things inside these objects. In some cases, on the close to disintegration, especially these. There's a couple of sledges inside. They look like this. The wood is rotting away to varying degrees, and it's primarily the cellulose which is lost because of the fragility of the glycosidic bonds. Lignин's a bit tougher, but even lignin has its own degradation profile. And actually, this piece of wood here, these white bits are residues of alum. And I think, as Jennifer explained before, the problem with the discoveries in Oslo surrounding the Osberg Viking ship was that the wood was preserved in waterlogged blue clay, but in order to stop the wood from shrinking as it dried out and destroying all the delicate carvings and things, the conservatives used alum, hot alum, which when it cools forms these rock hard crystals, which indeed stopped the wood from shrinking. So as a short-term solution, it worked beautifully. But what the conservators didn't know, that the process led to the production of sulfuric acid, which over the years has caused degradation. You can see this is Paul Johansen consolidating this the sledge, which is now under serious threat of disintegration. So 10 years ago, the curator of the ship museum in Oslo, that's Jan Bill, got together a team of polymer scientists and conservators, and I was one of those that was invited along. I think that's me there's Jan by the Osberg ship, to sort out a strategy for trying to replace the rotted wood fiber with material which was going to last for a long time, and also deal with the problem of the sulfuric acid and acid residues left in the wood. And the objectives been to develop like a toolbox of consolidants for the conservators to use, depending on the state of degradation of the archaeological wood and whether or not the wood had been prior treated with alum. Because if it had been treated with alum before, then that excluded, particularly for the more damaged materials, excluded the use of aqueous treatments, because aqueous treatments ran the risk of destroying the remaining alum crystals, which was in many cases all that was holding the wood together. So non-aqueous formulations had to be developed. So we call class 1 the aqueous formulations, polyethylene glycol. That's a petrochemical, so now there's a feeling we should be using this sort of stuff, and we should be using more bio-based or bio-inspired materials. So this group here, including terpenes, because you can get them as aqueous soluble. And then class 2, the non-aqueous, for things like the Osberg artifacts, chitosan. I mean, you can derivatize chitosans, aminocelluloses, to give non-aqueous properties, lignins, terpenes, and siloxanes. And I call class 3 archaeological textiles, and this is what Jennifer's been doing the last 2 or 3 years with a project led by Hartmut Kutzke, again at the Cultural History Museum in Oslo, and considerable progress has been made there, and the work is now being written up for publication, hoping to get an extension on that. So for consolidating archaeological wood, these are the ideal properties of a consolidant. First of all, what you want is a soluble, low viscosity resin, which is easy to infuse or inject, preferably based on natural products, bio-based or biological, or at least bio-based. To have an optimum, depends on the extent of degradation of what's being consolidated, but a sort of rule of thumb is that you want polymers of a molecular weight of 4 kilodaltons for injecting into the wood that can then be cured inside the object and interacting with the remaining wood material by hydrogen bonds or whatever to give a strong, highly stable network. There's no point putting something in which is going to degrade within a few years. It's got to be long lasting and also non-toxic, so it shouldn't be poisoning conservators or any visitors to the museum. So non-toxic and does not change the original appearance, color, and size. And the first class of molecules we looked at, again with Jennifer, there was some earlier work done before that, but that was one of the main focuses of Jennifer's PhD, were chitosans, which come from chitin, from the shells of crabsters, lobsters, and other crustaceans. And they're attractive because they have a similar backbone to cellulose, beta 1,4, and the amino groups, after you deacetylate the chitin to varying degrees to give chitosans of desired properties, desired solubilities and things, is that the amino groups are good at mopping up acid residues. So in principle, it can provide strength and also lower the acid levels of the wood. From a hydrodynamicist point of view, the attraction of getting involved with projects like this is that we can sort of flex our hydrodynamic muscles. And at the time the project came about, Gordon and I were working on chitosans anyway, for different reasons, for as biopharmaceuticals, basically. And so there were very interesting molecules to characterize. In the AFM, they come out with a sort of semi-flexible appearance, and the Mark-Howing coefficient from viscosity, molecular weight, and the persistence length, which we get from this height fit analysis, which is a combination of AUC, secmals, and viscometry data, and this persistence length here, all point to a semi-flexible molecule. So that's a sort of molecule you want, really. So it has some rigidity, but some flexibility in enabling it to interact better through hydrogen bonds or whatever with the wood material or whatever else is being injected into the wood. And then here's another flex of our muscles with determination of the molecular weight distributions using this method we developed called the extended Fujita method. And this is, don't embarrass Dalal, but this is Dalal's brother, Fahad. And part of his PhD actually was looking at the properties of these chitosans. So these molecules are too big as they stand to be used. But Jennifer developed a method using a combination of hydrogen peroxide and UV to reduce the size of the chitosans in a controlled sort of way to the size which we needed to inject into the wood. This also tied in with some other work we've been doing with Gordon on the controlled degradation of polymers. But chitosans tended to give sort of variable properties because it was very difficult to get a uniform degree of acetylation or deacetylation. And that's what you get with, particularly with natural glycans, polysaccharide-based materials. So there was a chance to use these other materials which are related to chitosans called amino celluloses, which are related to chitosans in the sense that they have the beta-1,4 glucan backbone. They have these amino groups coming off, and also these tosyl residues. In fact, it looks almost like a protein or polypeptide in some ways, except it's not a peptide bond here. This is these are glycosidic bonds, which is the backbone. So this was a collaboration with Thomas Heinz's group at Jena, which is still going. And not only do they look like proteins, but they behave like proteins because they seem to self-associate in a regular sort of way. Monomers, dimers, trimers, tetramers, pentamers, which was very unusual for polysaccharides. Not only that, they followed this relation between sedimentation coefficient and molecular weight, which we call the 2/3 power rule, which usually applies to globular proteins, not polysaccharides. So these aminocelluloses had self-assembly properties, which was good from an archaeological wood consolidant perspective, but also appeared to behave like proteins. And we published this paper in Angewandte Chemie on this. And from sedimentation equilibrium experiments in the autocentrifuge, these are diagnostic plots of number average, weight average, and cellulose molecular weights. And diagnostic if they all go to the same value at zero concentration, again, is symptomatic of a reversible association. And then we get this confirmed by overlaying plots of point average molecular weight against concentration in the autocentrifuge cell for different loading concentrations. So these are quite interesting molecules as far as polysaccharides are concerned. But the important thing was that they self-assembled. They had this self-assembly property, which would aid in the the curing process. Now, they're all water soluble, but then part of Jennifer's PhD, she looked at trying to get these the chitosans and the aminocelluloses to be soluble in non-aqueous solvents, and Jennifer was successful in that goal, and the materials were checked out, and also Jennifer looked at the at how they sort of reacted with the wood once infused into them, and using this technique known as SEM coupled to energy dispersive X-ray spectroscopy, she was able to show by appropriate labeling that the materials were coating the pores inside artificially degraded wood. I think that's correct, Jennifer. Correct me later. Oh, and then she also looked at the physical properties of artificially aged wood with these different types of consolidant. Okay, now an easy approach would be to just take molecules which are naturally soluble in non-aqueous solvents anyway, lignins or terpenes, and lignins, they can be extracted, and then there's the problem of having to reduce them to the desired molecular weight for infusion, and Yudong was involved in this project, where we looked at a range of different types of lignin, again in collaboration with Oslo and with a group at Wageningen. And these are some of the shapes of the lignins that we determined, which fitted an oblate disc shape of a model, which again would be very useful in providing a large surface area for interaction with the remaining wood material inside the degraded woods. But the problem again, as we found with chitosans, was in getting them to degrade in a controlled sort of way. So as with aminocelluloses, with the aqueous situation, terpenes provided the non-aqueous analog for this. And terpenes are a wide class of macro molecule appearing in nature. They have the general formula C5H8N for N greater than 2. These are some of the monomers which can be changed or tuned, we call, to give different functionalities. But the important thing is they can be linked to a polyacrylate or polyacrylamide backbone. So it's not entirely biological, but bio-inspired or bio-based, because the terpenes, which for archaeological wood consolidation, we get from pine wood, which is good. So we're actually using wood material as the basis of the formation of a consolidant. So these are natural, and they are coupled to a polyacrylamide or polyacrylate backbone, which are far more stable compared to the beta-1,4 glucan based backbone we have if we're using straight polysaccharides. And Michelle was involved with this as part of her PhD, and had some, like Jennifer with the aminocelluloses and chitosans, had quite a lot of success with with these. So this one here, TPA5, terpenoid acrylate 5. See it linked to the acrylate backbone. Looked at the properties of these, checking the molecular weights again. This is in isopropanol, which is a very friendly non-aqueous solvent we use. As I said at the beginning, we don't want to use solvents or materials which are toxic, especially with the public about in the museum. So in isopropanol, this one TPA5, this is the sedimentation coefficient distribution at a range of concentrations, and the molecular weight again comes out to be about 4,000, which is what we want. That's the ideal size for injecting into archaeological wood. And from this beta function here, which is we get from combining sedimentation and viscosity data, the range of beta values are consistent with a prolate or rugby ball type of ellipsoid, rather than the flat disc oblate which we got with the lignins. And these are estimates either from sedimentation or from viscosity, which all suggest the same sort of shapes. What you want, something which is sort of elongated to promote the surface or extra surface for interacting with the wood when the materials have been injected. And all the monomers for the terpenes have been used or generated, and again built onto an polyacrylate or modified polyacrylate backbone, TPA6 and TPA7. So these are the three terpenoid polymers that Michelle generated as part of her PhD. And TPA6 appeared particularly promising from the tests that were done on artificially aged archaeological wood. But there's a lot more to be done. And with terpenes, we can get them so that they are both aqueous or non-aqueous soluble. And because they are bio-inspired, bio-based, they are, if you like, environmentally acceptable or more acceptable compared to polyethylene glycol based materials which have been previously used to consolidate vessels like the Mary Rose and the Vasa ship in Sweden. So that's more or less it. We're just having the final discussions before making that final step of submission, and then you're literally in the hands of the gods then in terms of whether it's funded or not. But we're hopeful that this might stand a chance, like with Gordon's, because of the strong involvement of the our colleagues from Norway. And in this case, this is, I mean, the Osberg ship and things like this. This is Norway's national treasure. So if they all fell to bits, that would be bad. And again, if we got this wrong and put the wrong stuff in, which accelerated the decay, that'll be a disaster. But that shouldn't happen, because they won't let us near the real objects until everything's been fully tested. So that's the application that's going in. That's the old logo, which might have to be changed. It's be quick though, folks, because this application is going in quite soon. And the PDRA is for 4 years. If it's successful, that's it. Yeah. Okay. So that is our planned application to the EPSRC and the Norwegian Research Council. And should I stop sharing? Or has it stopped? Anyway.
You've already stopped sharing.
Yeah.
All right. Well, halfway through this, just now or halfway through the talk?
No, just now.
Okay. That's a relief.
Yeah. Sorry, Steve. You blacked out for the past half an hour. Can you repeat all that?
Right. Where did you get that sense of humour from, Richard? Wasn't from here, was it? Okay. So that's Jennifer. Many apologies. It's repeating what you said, and probably in a much worse way than you would have presented it. So hope you weren't cringing too much. Okay, but that's it. I mean, the thanks to Jennifer and Emily, Michelle, and Yudong, they provide the basis for getting a properly funded project, which will interact with Oslo's own. They've got their own internal funding for this as well, using the Saving Osberg program. So it's not going to cure COVID. It's not going to cure the common cold and things, but it's still interesting. And I got to pay VAT as well because it's non-medical research. Got to pay VAT, which is a big grouch of mine. Anyway. So that's anybody spot any howlers or things which need?
Oh, I think that looks super consistent, and I think it's the excellent proposal, especially with the considering that this is a scheme focused on the Norwegian UK partnership. I think with the history of partnership with scientific might, with the leverage that you get from Norwegians, I think, I mean, fingers crossed, but I think it stands a very good chance. I don't want to be sort of, but fingers crossed. Touch wood,
in Norwegian.
Touch wood, yeah. But yeah, I think that looks incredibly strong. And I think they're reflecting on the previous proposal that we've submitted, and then they were saying like, oh, it's like a scattergun approach when they say, oh, kind of, you don't know what you do, you try different things and try to jam pack all the different technologies. I think this is very much now addressed, and yeah, it's very focused. And yeah, there are different technologies that will be tried, but I think it is properly justified because what I think we didn't articulate, or what we probably didn't spend enough space to articulate, is the need for different technologies, for different even elements within the same artifact. So different degree of degradation, different degree of exposure to metals, different degree of even sort of whether they're in contact with any other materials and things like that, metal or whatever. All that requires slightly different approaches, and here you take a very focused but at the same time a comprehensive look at the available range of the technologies that might find their use. And as I say, it could be for a single artifact, you use a different conservation chemicals, because different parts of the same object may require different degree of restoration and preservation.
Absolutely, and with it being an NCMH application, so in fact the whole of the NCMH is involved with this. If it's successful, though, that's the key thing. And if you know any nice referees out there,
Steve, could I ask a question?
Yeah, go on.
When you do these treatments, is there a size limit on the material you can actually use? So, for example, if you've got a Viking ship, that could be quite a big object. Are there any limitations of how you do the treatment for the size of the material that you're actually using?
Yeah, I mean, we're not focusing on ships as such. It's the artifacts really,
Okay.
which can be immersed. Okay, you can't do that with a Mary Rose or something like that.
No.
These objects, you can immerse them in a large bath. So infusion, or okay, CPAP, it's infusion or injection. These are the two ways of administering the material into the wood, or spray. I mean, the Mary Rose, when that was being treated, was by this continuous spray, which it must have cost millions to do. Yeah, and in terms of the size of the polymers that can go in, again, it depends on the porosity. I suppose the more degraded it is, the bigger the polymers you can get in. But that's why, I mean, the stuff Jennifer was doing by monitoring to see if it actually had penetrated the wood, and you got those SEM EDS images to show that it had. Yeah, so that's why you got to have a toolbox. You have to have a variety of different materials of depending on the state of degradation of the material and what had been done to it beforehand.
Okay, thanks, Steve.
Okay, right. So, and then, as Gordon, I'm sure, will agree, after submitting the application, the rest is just left to the gods, isn't it, really?
It's waiting. I think Gleb and Richard have got some questions, though.
All right, sorry, Richard.
Gleb first.
Gleb, sorry, I didn't see the hands go up yet.
That's all right. So I think in terms of a very fundamental perspective, and going back to the hydrodynamics, I think we haven't talked much about the interfacial hydrodynamics, which is actually very important. And I think in this case, it is very important because this propagation of the wetting front is incredibly important, and the position of the macromolecules within the precursor film and this wedge of the liquid that actually sort of penetrates the porous media, which is an artifact, and wood is a porous media. So I think that would be really good to reflect on that, because there is also some literature and actually behavior of macromolecules in confined geometries. And I think that would be really reflect very strongly on the fundamental aspect of this project, apart from obviously the practical application and great sort of how it's called, the ambience, I mean, the precious artifacts and things like that. And there is very interesting chemistry there. But in terms of physics, I think that if that could be reflected a little bit more, I think it would strengthen further the proposal from the EPSRC perspective, and kind of what new physics we are discovering. And this is actually molecular hydrodynamics in confined spaces, which is something that is very interesting, and probably there are a lot of discoveries that can sort of be stimulated by looking at the behavior of these macromolecules within this complex geometry of the wetting front.
Absolutely, Gleb. I mean, the problem then is, how do you reproduce that ex situ? How do you reproduce these conditions outside the wood? So if you look at it in the laboratory, not inside the wood, it's very difficult to quantify. I mean, like the methods that you were using before, using the SEM-linked spectroscopic types of methods is one way. But yeah, any ideas along those lines, Glenn,
Using
would be
our
really
new
appreciated.
biofluidic microscope, the biofluidic microscope in NMR that is in NMRC, our Steve one that you are on the core eye on as well. You are.
Yeah,
You are
right.
on the ground,
It's still
Steve.
active, that one,
It's
yeah.
your chance of claiming, taking the credit because you are core-eye on this grant, and this would be a perfect tool to look at the confined geometry and the hydrodynamic forces in the confined. And we can make a cellulose particles, or even we can make like a colloidal probe, and then do the hydrodynamic measurements in the confined geometries. So
Okay, we need to speak. Me and you, Glenn.
okay, just let me know. I mean, when the project is when this goes in.
Soon, I think we've got a provisional case for support. Can be adjusted, and we're just doing the pro forma stuff. But it's not too late to change to alter what.
Well, it could be very short. It doesn't need. You don't need to alter. You just put a paragraph that this will be considered and evaluated and things like that. So it's just.
Yeah, because the more detail you give, the more you set yourself up for.
Yeah, that's true.
Attack by referees. That's what we found. We try to keep this quite focused and straightforward. But
yeah.
I mean, what you say is like what a referee would say. So I think that's important. We need to be aware of that. And if the facilities are here at Nottingham, then
they are.
That would be brilliant, because that would show that the infrastructure is here to do the project. Excellent. So there we go. Justified in giving this presentation. Thank you, Jacob, for getting your Medical Academy award and things, which is fantastic. But it's given us a chance to discuss and get some suggestions, which is fab. Good. And Gordon, you've not heard about yours yet?
No, I've not. I think could be some time. I was talking to a colleague who submitted about 2 months before me, and they haven't heard anything. Just a normal EPSRC rather than anything related to Norway. So I don't know if the Norway link will maybe make things quicker. I don't see any reason why it would.
Okay.
But so I think their new system is slowing things down. I think Richard and Jennifer have questions for you as well.
Yeah, Jennifer's got 2 questions. Richard, might Jennifer goes first because she's got two hands up. You need to.
No, it's not the hands.
It's Rich first. That's why it's the number 2. I was second to put my hand up.
Oh right, right.
So it is Richard.
There you go. Now you're first.
Ladies first.
It wasn't much. It was just to say that I was wondering with the non-aqueous chitosan, is that staying in?
No, we're taking chitosans out of the project, but it will be cross-referred to. So previous work on chitosans, which you did, would be referred, because the reason why we did that is last time we were criticised.
I mean,
for trying to do too much.
Well, I was going to recommend taking that out because it wasn't successful. I mean, it proved that the chitosan coated the cell walls, but it was too brittle.
Yeah.
No.
Okay. Thanks, Jennifer. So there's no second question then? No second.
No, but actually I do have one more. I was just wondering about the sporopollenin, if that was still in or not.
Oh yes, it is. I didn't mention that because we would have been here till midnight.
Okay.
Sporopollenins, these are nature's strongest polymer, which polyketide based structure with coumaral groups. It's almost lignin-like in its terpene-like actually in its properties. So but it's insoluble. So the idea is that in the project, for the terpenes to, so they're tunable, to try and build into them sporopollenin functional groups, so that you get the functional properties of sporopollenin, and yet can still solubilize the molecules in IPA or whatever.
Yeah, because I remember the solubility issues last time, so I was wondering.
Can't do it. We can't do it. We've looked at it. We can't do it. Okay, Richard, at last.
Okay, thanks, Steve. So I was just reflecting on it, and it feels like you've got this balance between you want a relatively big polymer, which is going to form the rigidity of the structure, but it needs to be small enough to actually penetrate. And so I feel like there's this balance, and that you need to get the chemistry right as well. The ideal, I suppose, would be to inject some sort of monomer and then get it to polymerize while it's in situ.
Yeah, that's it. Well, you put in your 4 kD and then get that to cure inside the material. And the chemists have got ways of, and the chem engineers, using microwave. There's only been a microwave technology. Obviously, you don't want to overheat or microwave, so you burn the whole ship museum down with a fire. You don't want that. But there's control ways of curing the polymers inside the wood, which EGP, I don't know the funny processes they've got. This is Rob's domain, really, Rob Stockman's. But yeah, that is important. The curing process within the material.
Mm. And then I've got a second thing, and I may or may not be joking, depending on how well this goes down. With products like Ronseal, right, where you're trying to paint a fence and you need the wood penetration, are they doing anything interesting with the chemistry there, or is it literally just paint?
I think does it contain acetone or something? Is it like a wood hardener? I mean,
because that's on wood that is like perfectly fine and it's not been sat around for 2,000 years.
No,
but yeah,
I think that's that's a sort of, and it doesn't last anyway. The Ronseal, it doesn't doing with time. I mean, before all this modern window technology and things, and that everyone's got now in their houses, but you used to have these wooden. It was a pure wood, and I don't know how many times I was up in a ladder, a house, injecting this acetone-based stuff into the wood that just gone like paper mache. It's just get mush. And no one else is. Oh, Tony will remember. Tony might remember that sort of thing. You're old enough to remember rotted wood sills and things, which we had to get up ladders to repair.
Yeah, a long time in the past, Steve. Yes.
Yeah. So yeah, that's good point, Richard. Good point.
fair enough.
So we're not. Yeah, I'd like to use Ronseal, but can't really.